After chapter 1, when we've started talking about units and measurements and calculations, the interesting thing is to try and figure out what order of topics to talk about. And chapter 2 begins with some information about the atom, but this is always a little awkward because the reality is that scientists didn't discover the atom for a long time. And so it actually, to me, makes a little bit more sense for us to jump ahead a tiny bit and then we'll return and talk a little bit about chemistry as a science and also the development of the periodic table. Now, I want you to cast your mind back multiple hundreds of years, let's say about 300 years. So we're in the 1700s, and there's been science going on for quite a long time. If you might remember, you have folks like Copernicus and Galileo discovering some incredible stuff about the universe. And you also have lots of interesting mathematics going on. And there's tons of science, but the problem with the science, with a lot of the science before the mid to late 1700s, is that a lot of it was really a lot more like philosophy. People would sit around and think about it, mostly men, mostly wealthy men, and they would think about what they thought was true about the universe, and they wouldn't necessarily go out and do a lot of testing. And we understand the scientific method to be a process of thinking, making observations, collecting actual measurable data, and then rechecking our evaluations. So this really starts getting started in the mid-1700s with Antoine Lavoisier, who was a French nobleman and also a rich man. So he had the leisure to construct or have people construct and build equipment for him to take data. But the interesting thing that didn't get talked about much at the time is that his wife, Marie-Anne Paul Lavoisier, was also really active as a collaborator with him. And this painting of them by Jacques-Louis David is really significant to me for that reason, because if you look back at the history, Marie-Anne was working with Antoine in the lab. She took very careful notes. She recorded the experiments. She drew diagrams. She did translations. So they really worked very collaboratively in the lab to do the science together. And she was responsible for making sure that his work did not get destroyed after his death, and that it got published and circulated. So she's probably the reason why we know about him. Anyway, Antoine Lavoisier and Marie-Anne Paul Lavoisier worked very hard at making sure that their science was using the scientific method, like we would imagine. And what's really fun, if you ever get a chance to go to Paris, is to visit the Musée des Arts et Métiers. So it's a Trades and Measurements Museum. And you will find there the laboratory equipment of Lavoisier. And my picture here is not super duper in focus, but here's a slightly better one. You can see these were all handmade machines that he used for doing scientific experiments. And so Antoine Lavoisier is really known as the father of chemistry because not only did he do all of this science in a very careful and dedicated way, but he created the first chemistry textbook, effectively, which you can still read. You can find it for free on the Gutenberg Project, and it's called The Elements of Chemistry. And I have the English translation here because I don't speak French very well, but this quote that I have here, I'm going to stop and let you read it in just a moment. This quote is from his introduction, and it really describes the process of using the scientific method when nobody else at the time really was using the scientific method. So I'm going to stop talking and please read it. I'm a fast reader. If you need more time, please go ahead and pause the video. But if you've read it, I find this quote to be really inspiring, that here's this guy 250 years ago, and he says, I'm always going to draw conclusions only if I have evidence backing them up. And that's really what we're talking about when we do the scientific method. We find evidence to back up whatever conclusion it is that we're going to do. If you have time, look up this book, Elements of Chemistry. What's cool is that Antoine Lavoisier, even before anybody knew anything about what an atom was like, he did these really careful experiments that allowed for the discovery of a number of different properties. So Antoine Lavoisier carefully measured the masses involved in decomposing mercury sulfide, which is a solid, it's a red solid. And when you separate it out, it turns into liquid mercury and into gas. And so he did these careful research that allowed him to measure the masses before and after this experiment and confirm that the law of conservation of matter works. So the law of conservation of mass or of matter is often attributed to Antoine Lavoisier because of his work. He wasn't the only person who kind of figured these proportions out, but the work that he did was really notable at the time. Okay, so chemistry really gets its roots in the practice that Antoine Lavoisier was doing in the mid to late 1700s. Now, unfortunately, if you have studied some European history, you might remember that this is also about the same time that the French Revolution was happening. And unfortunately, Antoine Lavoisier and his father-in-law, Marie-Anne Paul's father, were both arrested and were ultimately executed. But we can focus instead on the accomplishments rather than the tragedy of unjust things that have happened in the past or that are even happening now. So we have this establishment of chemistry as a scientific practice about 250 years ago. This really revolutionized it because before that there were all of these theories about things like phlogiston and pseudoscience stuff. You can look it up if you're interested. So one of the things that Antoine Lavoisier did, and if you read the Elements of Chemistry, it's super interesting to read about his analysis of air. He was able to separate by burning the oxygen. He was able to separate out the components of air, at least the two major ones, oxygen and nitrogen. And he figured out that oxygen is the one that we need for life, to breathe. And that nitrogen, if we are exposed to just nitrogen alone, we can't breathe it. And so he even figured out a pretty good ratio of these two. He figured out that the oxygen was about 1/3 and the nitrogen was about 2/3. He might have done 25% and 75%. I forget actually. But the neat thing was that he did all of this without actually knowing what nitrogen was. Nitrogen gas had not yet been discovered at the time that he was doing this research. And although the discovery of nitrogen is credited to Priestley, I think Antoine Lavoisier could just as easily be credited to it. At any rate, let's fast forward about 80 years. As you might imagine, we have a whole bunch of research that's been going on. And of course, we also have a lot of elements that have been understood from antiquity. Things like gold and silver and sulfur, lead, copper. Many of these elements have been known from antiquity. And there's been lots of different studies of what these different chemicals can do, but lots of elements have yet to be discovered. So in the mid-1800s, we have Dmitry Mendeleev, who is a Russian scientist, and he was reading all of these different articles by people who had done research on the elements, looking at their chemical properties. And it was Dmitry Mendeleev who put together this organizational system, who noticed that some of the elements react in similar ways to other ones. And so he is credited with organizing up the elements in the first periodic table, which he published, this is his scratch work, in 1869. And so 2019 was the 150th anniversary of the periodic table. And what's interesting about this periodic table is that the elements were organized by their properties. So the ones currently you might notice if you've looked at the periodic table recently, that this is rotated 90 degrees from what our modern periodic table is. That we have beryllium, boron, carbon, nitrogen, oxygen, fluorine, sodium, all in a column rather than all in a row. So shortly thereafter, after he published this version, he actually flipped it 90 degrees, and it became much more like the periodic table that we have now. So you can notice that all of these element symbols are the same as they were, and there are some deliberate gaps, like right here, that that Mendeleev left in the periodic table. He said there should be an element here, even if we haven't discovered it yet. We should have some elements here, and I think that they will eventually be discovered. So there's some very interesting work that he did on the periodic table. And while he didn't have everything right, he did get a lot of things right, and the organization of the elements, this is the first time anybody had put together this whole organized setup for the elements in the periodic table. So even this modern periodic table, which looks a lot like what we just did, I'm going to go ahead and scroll back and let's look at one particular area. Okay, let's look at this column 1, lithium, sodium, potassium, copper, rubidium, silver, cesium. Let's go down. Lithium, sodium, potassium, no copper. Rubidium, no cesium. Right here is cesium. And then francium wasn't on his list, which is totally understandable. It's a radioactive element that mostly people don't see. So the modern periodic table has its roots in Mendeleev's periodic table. And if you've studied the periodic table at all, you know that there's lots of information that's packed into this periodic table. But before we talk about that, I want you to look at this periodic table just for a minute and notice that each one of these elements has a number. Each one of these elements also has some letters that are associated with it. I've chosen to put a fairly simple periodic table on here. You also will find masses that are underneath, so additional numbers that are underneath our single-digit integer number on these. And then this periodic table has some color coding indicating something, right? It must be indicating something. So when we go forward this week, I'm going to give you a list of some elements that I'd like you to learn because we use them all the time. You don't need to memorize their numbers. I just want you to get familiar with their elemental symbol. That's what the letter is that's on each one. It's usually an abbreviation of the name, and sometimes it refers to a mineral name. And I just want you to get familiar with some of the most common elements like carbon, which has its letter C, its elemental symbol C, because we're going to use them all the time, and it's going to be really important for understanding things like short versions of chemical compounds and so on and so forth. So packed into this periodic table, we have a lot of classification going on, and I've put up a bunch of the vocabulary that you might hear when people are talking about the periodic table. On this week's worksheet, I'm going to go ahead and have us practice identifying what some of these things are, and if you find more classifications that belong on this list, you can certainly add to this list. So we will talk about basic classifications, the group, and period or row. Sometimes you hear family. I probably should have put that on this list too. And we'll also talk about blocks on the periodic table. And we will understand why these are S, P, D, and F blocks a little bit later on. Then columns on the periodic table often get classified as noble gas, alkali metal, alkaline earth metal, halogens, chalcogens, and pnictogens. These are all classifications of different columns on the periodic table. Transition metals, heavy metals, semi-metals, these are all different kinds of ways of talking about types of metals. Of course, you'll also hear people talk about classifying them as solids, liquids, and gases. But there aren't actually very many liquids on the periodic table because they're always at room temperature. So I'm going to pause this video here, and I'd like you to start looking at that worksheet that will soon go up to start thinking about the periodic table and what you can learn from it so we can begin familiarizing ourselves.